Section 5.5, our final section for this course, is the substitution rule. And this is an integration rule that allows us to essentially undo the chain rule. So now we don't think of it that way. We'll usually think of the substitution rule as a means of finding the antiderivative for a function, well, that's just written in a form that sort of lends itself to this rule. But what it actually undoes in the background, or what we're guided by, is the chain rule. So if you recall the chain rule, if we took the derivative of these nested functions, ddx of f of g of x, then we'd have the derivative of the outer function f prime of the inner function times the derivative of the inner function. That's our standard chain rule scenario. So what we'll try to do in order to find the integral of a function that might look like f of g of x, or actually, sorry, the integral of a function that might have the form f prime of g of x times g prime of x, we'll know that if we integrate both sides of this equation, that the antiderivative will be the one on the left, right? So this will be f of g of x. So what we'll look for often is if we have a complicated function and a composite function, namely, and we see the derivative of some inner function multiplied on the outside of some other function, then we'll know to try the chain rule. So what we'll do is typically say that this will be u, and then this will be u prime, or u prime we'll start to call du, the differential u, and we'll see how that goes once we jump into the rule. So here's a good example of that. This really throws us right into the standard type of problem that we'll see with substitutions and integration by substitution. So we're asked to find the integral of 2x times the square root of 1 plus x squared dx. So far, we don't really have any special tools for finding integrals. This is an indefinite integral, so remember that it's basically an antiderivative. That's what this notation now means. So since it's not an immediate antiderivative of something, right, or since it's not an immediate derivative for a function that we already know, we don't know its antiderivative. So the idea is this. I look a little closer and I see I have a more complicated function here, the root function. And then inside that, I see a function 1 plus x squared. This is playing the role of g of x up here. Because if I look really carefully and think about it, 1 plus x squared, the derivative of that with respect to x is 0 plus 2x, or 2x. So there's the derivative of this function outside the radical function as a multiple. So there's g prime of x. It occurs out there, and that's the main thing to see. That's the crux of this method, is to recognize when you have an inner function that's complicated, but you have a multiple of its derivative on the outside. And really, it's just a lucky happenstance that this comes about. But nonetheless, plenty of problems are solved with substitution. So what we'll do is say, well, let's let this whole complicated expression be equal to u. And on the one hand, we'd really like that to be the case because the square root of just u is u to the 1/2, and u to the 1/2 has a pretty easy antiderivative. We just use the power rule for antiderivatives. So our first step is to write u as 1 plus x squared, and we'll be able to swap that out down below in just a moment. But for now, let's focus on what we do with this u substitution. U prime is 2x, right? I take the derivative of this function, and I get 2x. Oftentimes, maybe your workflow in a substitution integration or any integration problem that you might be facing is you might just say, well, this is my complicated part of the integrand. Maybe I'll try to make a u substitution for it, and then I'll do that, write it down, and then take u prime and see if I can match that to any terms or similar enough terms elsewhere in the integrand so that this substitution might work. So anyway, in this case, what we have is the following. We realize that when we take u prime from this line here, we get 2x. So that's going to match. So 2x will now become u prime, and this will be the square root of u based on these two lines right here. So if I write down my integral I as being equal to the integral of u prime times the square root of u. Now, notice that I still have a dx in here. We didn't do anything to change the dx. Okay, but the most simple way to see this come about is to just watch the following steps. Notice that u prime is actually du dx. And in fact, it's probably better to write this as du dx every time from now on, because we're going to want to use these differentials in this expression du dx. So that's a useful thing to have around. Nonetheless, we've done it in this step, and what we see is that we have this nice algebraic property, more or less. This is actually the reverse of the chain rule, but it's nice to see that these essentially cancel, and that's the way we can treat them when we're dealing with these problems. Again, it's more the chain rule at work in there, but nonetheless, it works as it appears to work. So now we have the square root of u du. Well, that's u to the 1/2 du. Now that my differential matches my function's variable, in other words, we're in terms of u and we're in terms of du, I can now integrate this. Notice when I was here, I can't integrate this function, right? The dx does not match the u variable. This has to become du. And we were able to do that by canceling those two with each other from the u prime. So at this point, now we just use the power rule for an antiderivative of u to the 1/2, and we get u to the 3/2 and divide by 3/2, which is a factor of 2/3. Add plus c, my constant of integration, and then at the very end, we back substitute for u. Remember that we introduced u, we need to get back in terms of x, and u is equal to 1 plus x squared. So u becomes 1 plus x squared. It's all raised to the 3/2 and all times 2/3, and then plus c. So there it is. Maybe that's a slow, sort of labored version of the substitution rule. It's to sort of more or less introduce the intuition behind it. This is what we're thinking. Most of the time, you'll probably just try guess and check. I'll set u equal to this, take its derivative, and see if I match anything on the outside, right? Or if I match at least close enough, and we'll see what I mean by close enough. So let's roll on to the next example and see the formal substitution rule while we're here. So the substitution rule is that if u is equal to g of x, and that's a differentiable function whose range is an interval I and f is continuous on that interval. So all these conditions for the regularity of these functions. So assuming that they're all differentiable and all these things work out, then the following is true. F of g of x times g prime of x with respect to x, that integral, is equal to the integral of f of u du, provided that, it should say, provided this integral exists, not the limit. So fix that on the fly, provided this integral, which is essentially in the background, it is a limit, right? It's the limit of sums of rectangular approximations, but nonetheless, if it does exist, we say that f is integrable on a to b. So just as we always have. So basically that is our substitution rule. So what we'll try to do every time is take a more complicated function like this, match an inner function's derivative with some outer function, and hope that it works out. And then u is equal to g of x, and g prime of x dx becomes du, right? And then this term just becomes f of u. And then we're able to integrate a more simple function, just the function f of u. And hopefully that's one that we know how to take the integral of, with our chart of antiderivatives at this point, or any other integration techniques we might learn later on. So remember, keep in mind, u prime is equal to g prime of x. And better than writing u prime, I'll write du dx. And then I solve for the differential du, and I get that it's g prime of x dx. This is why we did that work with differentials back in chapter 4, right? Because now we can move these differential terms around, and what we see is this: g prime of x dx, this term, is equal to du. So that's how this du gets swapped out. It's g prime of x dx, thanks to the fact that u is equal to g of x. So that's how that term simplifies, or the other way we can think about it is when we put in u prime here, because it's equal to g prime of x, then we have a du dx and things cancel. Okay, so anyway, those are some of the background details. Using the rule, you don't quite need to know all of that, but this is really what gets us through these things. So it's good to recognize every now and then how this is actually working out in those details. So compute the indefinite integral. We're given x to the fourth times the square root of 1 plus x to the fifth dx. So what I'll try is just the same thing each time, right? It worked last time. I focus on the function that's underneath the radical, and that's 1 plus x to the fifth, because if I can make that just a single term u, then I've got u to the 1/2 power, and I can find that antiderivative. So I write that down over here, right? Again, other choices for u could have been x to the fifth, but then I'd have 1 plus u underneath there, and I wouldn't quite know what to do there either. I could try u equals x to the fourth, right? We have lots of liberty here to choose, and that's what makes the problems possibly difficult, but you also have that flexibility. You'll start to learn the pattern. Look inside the outer function for your u substitution. It should always be sort of stashed in an outer function, a root, a cosine, a rational function, 1 over, something like that. So with this u substitution, this u value, du dx is equal to 5x to the fourth. We've just differentiated 1 plus x to the fifth. Okay, so we have 5x to the fourth, and I'll solve for du here, right? By multiplying both sides by dx. And what I get is that du is equal to 5x to the fourth dx. And I'm feeling pretty good about this situation, right? I can look at this and say I need x to the fourth and dx to be in, in play in this integral, and here it is, right? Underlined in red is the x to the fourth and dx, right? So that's equal to du except for this multiple of 5 that's down here. So that's the only thing that's kind of slowing me down. Well, that's not really anything that I need to worry about too much other than to clean up my terms. And that's going to look like the following. Let's divide both sides of this equation by 5. And I get 1/5 du is equal to x to the fourth dx. So that's a perfect swap, right? 1 x to the fourth dx, that's exactly in here as these two terms. And I can swap them out as 1/5 du. And the 1/5 really won't make that big of a deal because it's a constant and I'll be able to factor it out of the integral. Now you see off to the side, I've done an alternative method in blue, and you might try this out on your own. You could do a direct substitution for dx, writing it down as 1 over 5x to the fourth du, and then you substitute that in for dx here. So you'll now have a du in the equation, and you'll have a 1 over 5x to the fourth. And what you're hoping is that all of the x's cancel out when you do things in this pattern, in this method. And you see that this 1 over 5x to the fourth will cancel with x to the fourth, and you'll just be left with 1/5. So either of those is fine. Let's go with this one. It's a clean swap. I think most students prefer this because they'll write it down, sub in dx, and then hope that all the x's cancel out. When that works, you know you're good to continue with the problem. So here is our substitution for dx in the integral. It's now 1 over 5x to the fourth du. And I guess what I've done is I've done the blue version. So, okay, nonetheless, there we go. So x to the fourth cancels. We have 1/5. We factor that 1/5 out front. Square root of u is the square root of 1 plus x to the fourth. So, right, that was a nice clean swap. That this portion is always easy to swap out. And I have u to the 1/2 du. That's u to the 3/2 with a multiple of 2/3. And that's times the 1/5 that was already there. And we get 2 over 15 u to the 3/2, or 1 plus x to the fifth to the 3/2. Well, I guess I should have said x to the fifth, not x to the 1 plus x to the fourth. It's 1 plus x to the fifth plus c, right? We always add that constant of integration. As soon as the indefinite integral goes away, we put a plus c. And there we have it. So, yep, there's in blue, that's the method that we have right here, making a clean substitution term for dx by solving for dx. Or we could otherwise realize the same thing by saying, well, 1/5 du is equal to x to the fourth dx. If I pull out x to the fourth and dx, I'm going to be left with 1/5 du. And that's exactly what we have when you look here, 1/5 du. This term's just doing its own work, changing the radical to a power. So let's see some more. Practice with this and getting some more exposure to different examples will really start to bring it, we're going to do an intuitive state. So let's see, calculate the indefinite integral sine of natural log of x over x. This looks pretty complicated, possibly a little daunting. It might help every now and then to rewrite terms and rearrange things. If you get stuck, shift terms around and see what you might find from doing that. So sine of natural log of x divided by x, well, it's the same thing as saying 1 over x times sine of natural log of x. And maybe you saw it before, but maybe now this helps you to see it better. I have an internal function of natural log x. Its derivative is 1 over x. So here's a factor of that. That's perfect. If I set u equal to natural log of x, well, then du will be 1 over x, or du dx is 1 over x. And dx du, well, it looks like dx du is x. If I solve for dx, I get x du. Another way to put that. So again, u is natural log of x because that's my inner function, right? You don't really choose these other functions. You don't choose sine, that's the outer function. You don't choose 1 over x because it's not a nested function, really. It's not an interest. Or if you did, you might choose it and then realize, well, its derivative is negative x to the negative 2, and that looks nothing like anything else I have. So natural log of x, you just kind of test. You look for an inner function, take its derivative, and then you check to see if it matches something. Here it did, so we're off and running. So u will be natural log x. Its derivative du dx is 1 over x. And just to shift this, so dx, so let's flip both sides, take the reciprocals, and we have dx du is equal to x, right? Or x over 1. So I flipped both of these fractions in order to solve for dx. Dx then is equal to x du. I multiply both sides by du, and I get x du. So now I have a clean swap. Dx is equal to x du. So I come down here, and that's what I'm going to do. I have the integral. My integral I is equal to 1 over x, that's my first term, sine of u, because u is natural log x, times dx is now x du. And it's at this point that I realize the x and the 1 over x multiply together to cancel. That's what I was hoping for. The x's have got to go before I can actually move forward with this integral. And it looks like both x's cancel out, and I've got integral sine of u du. And now I'm all set to take the antiderivative of this function. The antiderivative of sine of u is negative cosine of u plus c for my constant of integration. And then lastly, I need to back substitute my u is equal to natural log of x. So I swap that back out for natural log x. And there we have the final, or the solution for this example. Next up, we scroll down to a rational function, it seems. So now a rational function, think of it like this. Again, I've kind of decomposed this because maybe I look at this and I'm just not sure. One thing that comes to mind is, well, if I take the derivative of just the bottom there, I get 0 plus 18x. The key thing is that I get an x, and that matches my numerator. If I didn't quite see this as two different functions, I might look at it like this. Factor the x away from the numerator, so you just have a 1 up here. And the x is sitting here now. And this is 1 over 1 plus 9x squared. This is a composite function. The outer function is 1 over something, the reciprocal function. And the bottom, well, or the inner function is 1 plus 9x squared. So this is a great candidate for a u substitution. Again, I might guess and check here, right? I might try u as x, and that doesn't work, right? As you start to learn this method, you're going to choose wrong sometimes. You won't always choose the correct thing. You might just choose 9x squared as u. But the problem with that is you'll try to take the antiderivative of 1 over 1 plus u, if that happens to work out for you. And 1 over 1 plus u doesn't have a very obvious antiderivative. It's got to be an obvious antiderivative at this point because we don't have any other tools. So u is going to be 1 plus 9x squared. And what do we do with u? Well, first things first, we take its derivative with respect to x, and we get du dx is 18x. So then we want to solve for dx. Well, I'm going to divide both sides by 18x and multiply both sides by dx, and this is the result of that. So du dx is equal to dx is equal to du over 18x. And I come back to this and say, okay, well, my integral is now x from here times 1 over u from here times dx is du over 18x. And I write all this in, and what I see is that once I've done that, I have an x in a denominator, an x in a numerator here, or x on top at least, or not in a denominator, and they cancel. So the x's have canceled out, and now I'm looking at the antiderivative of 1 over u with respect to u, or the integral of 1 over u with respect to u, and I have a constant of 1 over 18 that I just factor out of the integral. So it really doesn't matter. The constants, if the constants don't match when you do your first eyeballing of this, when you do your first sort of sketch, that's okay, as long as the degree of x's match. And when you take the derivative of this thing, you get 18x, and that matches x's degree. So you know that it's probably going to work out. So anyway, the antiderivative of 1 over u du is natural log u. Remember, natural log's derivative is 1 over its argument times the derivative inside its argument, but this is a simple version, so there's not much to do there. So we have 1 over 18 natural log u plus c, and then u needs to be swapped out for 1 plus 9x squared, because that's what we set u equal to start with, and we now have our antiderivative. So remember that all these antiderivatives are pretty easy to check. These indefinite integrals are pretty easy to check. You just take the derivative and see that you get back the function that was in the integrand. So there we have it. So more examples. It won't hurt to see all these. This is actually a simpler example than what we've dealt with before. But now I have e to the negative 2x. It looks pretty obvious that my only choice for an inner function is negative 2x, right? E is the outer function. Negative 2x is stuffed into its argument. So u is probably negative 2x. So we go with that naturally. So then the derivative of u with respect to x is negative 2. And then solve for dx by multiplying it on both sides and dividing by negative 2, and we get dx is equal to du over negative 2. So now I go back to my original integral. It's now equal to e to the u, because u is negative 2x. And dx is equal to du over negative 2. That was this line down here. So all I really introduced is a factor of negative 1/2. So I can factor that out of the integral as a negative 1/2. I'm taking the integral of e to the u du, or finding the antiderivative of e to the u. Well, that's just e to the u. E is its own derivative, or e to the u or e to the x is its own derivative. So there we have that, plus c. The last move is to write down u as negative 2x. That's what we set it equal to in the first place. So be sure to back substitute and come back in terms of x. And there we have it. Now notice you might not always need to use the whole substitution rule to take these antiderivatives. If we took another antiderivative of this function, we can see pretty easily that we're just going to pop out another factor of negative 1/2 times this factor of negative 1/2, and that antiderivative is going to be 1/4 e to the negative 2x, right? And we can start to do some of these mentally, but we didn't really have the structure to work with, or the tools to work with to find these antiderivatives until now. So we will get a lot of simple ones out of it, as well as some tools that'll help us through complicated problems. Okay, so now let's do something a bit more interesting, right? Let's calculate the antiderivative of cotangent of x. Let's apply this to some trig functions. We already know the antiderivative of sine of x and the antiderivative of cosine of x, but this is a little bit less known. We can find the derivative of cotangent of x. We've learned all those differentiation rules, but we don't exactly know cotangent of x's antiderivative yet. So let's meet that. So the first step to calculating this is to write cotangent of x as cosine x over sine x. So there we've done that. And now I'm going to factor cosine of x out of the numerator. I don't have to, but that might help me see things a little better. What it tells me is I've got this sort of multiple function here off to the side, and I've got a nested function here. I've got the reciprocal function, 1 over something, and in its argument is sine of x. So my candidate for my inner function is u equals sine of x. So let's see how that does. Go off to the side. If u is going to be sine of x, we probably realize it right away. If u is sine of x, well then du dx is cosine x. That's going to match the other term that's in this, right? Or as we see over here, 1 over u times, well, cosine x is here, so that's going to be our du. But once I solve for dx in this expression, I get dx is du over cosine x. That's how we'll see that this thing cancels, right? So cosine x times 1 over u, because u is sine over x, and then du over cosine x is dx. Right, so we found down and left. So, and then we see again that all the functions of x cancel. Cosine x over cosine x is a 1. I'm looking at 1 over u du as my remaining terms in the integral. And that's a pretty easy integral to do. And that's our evaluate. That's the natural log of u plus c. And ultimately, u is sine of x. So it's natural log sine x plus c. Now, we might see this written in other ways. In order to connect cotangent of x to cosecant of x, since they're often linked type functions like secant of x and tangent of x are, what we might do is this. We realize that sine of x is actually 1 over cosecant of x, or cosecant of x to the negative 1 power. And since that's a negative 1 power, we can use our logarithm rules to take it down from the exponent and multiply it against the natural log. So it becomes a constant outside the logarithm. So we end up with negative natural log cosecant of x. Now notice these two answers are in fact the same, but books will commonly give you this bottom one down here rather than the one that we initially found. So just keep that in mind if you're trying to check your answers. I've also introduced here an absolute value, and that's because when we take the antiderivative of 1 over u, well, we'll typically express that as the natural log of the absolute value of u, right? And the book might go into the details of that in this section. If not, that'll come in a later calculus course, why exactly we do that. But if you remember, natural log is only defined for u values that are positive, right? Or for values that are positive. So we have to make sure anything that goes in here is positive. But what you'll find is that even on the negative side for these u values, this still gives us the correct antiderivative, interestingly enough. So lastly, let's have a look at the substitution rule for definite integrals. There's not much going on here. What I recommend you do is this. In an easy case, just find the antiderivative, right? So this first example, just find the antiderivative, capital F, right? And then apply the limits of integration or evaluate at the limits of integration. So here's the easy version. I'm ignoring this rule for now, but I'll show you what we can do later here. You just find the antiderivative by carrying out the indefinite integral. Well, it's negative 1/2 e to the negative 2x. We've already done this one in an example in the previous page. So now I pick this function up, and I know that if I'm going to look at the definite integral, I just need to evaluate at my limits of integration. So my integral here is equal to capital F of 5 minus capital F of 1, where this is capital F, my antiderivative. So I have negative 1/2 e to the negative 2 times 5, being the x value. And then I have minus f of 1, which is negative 1/2 e to the negative 2 times 1. So f of 5 minus f of 1 written down in terms of the antiderivative function, capital F. And then, well, simplifying this really only takes us this far, and then we're done with that. So when it's simple, then you can just evaluate directly. Now, what this thing above is telling us is the following. If we have a definite integral, and we're going from a to b, f of g of x, g prime of x dx, and u is equal to g of x, when we swap out our variables, remember that A and B are written here. They're in terms of the x-axis. dx is little increments along the x-axis, not the u-axis. So A and B are values on the x-axis. U is a function g of x. So u values are sort of filtered through the function g from x values. So if we're going to write f of u du on this side, then we need to go from g of a to g of b, because remember that f of u is f of g of x, right? So if we're just going to straight u values, increments of u here, then we have to make sure that we start at the same values, g of a on the left, and the same values, and end at the same values, g of b on the right, for f of u. Okay, and maybe this will make more sense in the example as we see what the details point out to us. So let's look at the bottom here. It says, evaluate the definite integral, the integral from 1 to e of the function natural log x over x dx. Okay, so this is a little interesting. It looks like probably a good practice would be to say, well, let's break up the rational function and see what we can do with it, right? So I write it as 1 over x times natural log x. And well, if my u is x, then I have 1 over u, and well, the derivative of u equals x is just 1. So I'm not really going to get anywhere with that. So what I try is this. I let u be natural log of x. And if u is natural log of x, I know that natural log of x's derivative is 1 over x. So that works out just fine. I see natural log of x's derivative as a multiple in my integrand. So that's the substitution I want. So I'll write that down off to the right. And u is equal to natural log x then. So du dx is 1 over x. And then I solve for dx to get x times du is dx. And I'm going to substitute x du in for dx as well as u for natural log of x. And what does that look like? Off to the side here, I have 1 over x, that was, originally there, times u, which is natural log x, times x du, which is dx, right? X du is dx. So in this expression, what I see is that x and 1 over x cancel. So this looks like it's going to work out. So I'm off and running and happy about it. But here's something I've done. I've denoted that these are x values. This is a 1 with respect to x, not u. So I need to be careful about that. So what I wrote here was just x equals 1 to e. And really I could say x equals 1 to x equals e. I'm just leaving myself a note. This is fairly unconventional notation. I'm just leaving myself a note so that I'll be able to recall to come back and put these values in terms of u instead of plugging x values into u variables. All right, so that's the main thing I want to avoid. I cannot plug x equals 1 into this u once I've integrated. So what do? Well, this should be u of 1 and u of e, or g of 1 and g of e, right? U being g of x, and that function specifically in this case being natural log of x. So to fill in for u of e and u of 1, I'm going to have u of 1 is equal to the natural log of 1, which is 0. I'm going to have u of e is equal to the natural log of e, which e to the what power is e? Well, e to the 1 is e, so natural log of e is 1. So I have from 0 to 1 in my u variables now, right? So now my limits of integration go from 0 to 1, and those are values of u. That's what u of 1 is. That's what u of e is, or g of 1 and g of e if we want to write g of x instead of u depending on x. So 0 to 1, u du, this is now very easy. The antiderivative of u to the first power is 1/2 u squared, and our limits of integration are from 0 to 1. So that's evaluate at 1 minus the evaluation at 0. And I get 1/2 times 1 squared minus 1/2 times 0 squared. And that all comes out to 1/2. So we've done this both ways, right? If you have a u substitution within your integral, and you're writing it as a definite integral, then you do need to carry out this change of variables, right? You need to swap it out if you're going to write it as a definite integral. But you could probably also do this problem the way that we did the one above it and just say, well, rather than do my integration with the definite part of the integral, I'll just do it as an indefinite integral, and then I'll come back and do my evaluations at the limits of integration. You could do the same thing here. Just find this antiderivative without these limits of integration, and then come back and write down the definite integral to find the actual value that they want at the bottom here. Okay, but it's good to know this because this is going to be handy later on in Calc 2 and Calc 3 when we're dealing with change of variables and integrals and things like that. We're going to want to know what actually happens in the background here in an abstract general case like that. Okay, so some tricks. So we have symmetry that we can exploit for functions, right? So let's see. Suppose f is continuous on the interval negative a to a, on a symmetric interval, in other words. So that's suspicious already. If you see something going from -5 to +5 in the integral, you might think about finding a trick for it. So if the function f is even, then the integral from negative a to a of f of x dx is equal to 2 times the integral from 0 to a of f of x dx. So rather than integrating the full interval, we just double and integrate half the interval. Right? We double the value of the integral and integrate over half of the interval. Okay, so what does that look like and why does it work? Well, here's negative a to a for f being an even function. Remember, it has symmetry about the y-axis. So this region here is actually equal to this region here. So instead of integrating from negative a to a, I could just integrate from 0 to a and then double that value, and that'll be equal to integrating from negative a to a because both of those highlighted patches of area are equal to each other. So that's how this one works out. That's the picture behind this identity. On the other hand, if we go from negative a to a for an odd function f of x, then its integral is going to be 0 in the end. Why is that? Well, remember, an odd function, or here's an example of an odd function. From negative a to a, maybe our odd function is in this arrangement. We have negative area here, and that's equal to positive area here. Remember, odd functions have symmetry about the origin. So 180-degree rotation, right? So we rotate this axis to here, and both of these sections match up with each other, and they're the same amount of area, only this one's under the x-axis and this one's above the x-axis. So when we add those two areas together, we get a net area of 0. So if we have an odd function and we're integrating over a symmetric interval, negative a to a, then we know that our answer is 0. Okay, so evaluate the definite integral from negative pi over 4 to pi over 4 of x cubed plus x to the 4th tangent x dx. So the alarm is this, right? The little indicator is we've got a symmetric interval. Maybe, just maybe, we get lucky. We have to check whether or not our function is odd or even. Hopefully it's odd, because I really don't see immediately a way to integrate this function. It looks pretty complicated. So as a student or somebody trying to solve this problem, I would really hope that this is an odd function. So far, it looks like it might be odd because this part of it is odd. Definitely no x cubed is odd. What I'm not sure about is x to the 4th times tangent x. How do we determine whether or not this function's odd? Well, here I write the function down. F of x is x cubed plus x to the 4th tangent x. And then I write down f of negative x. I very carefully put parentheses around all these x's and swap in a negative x inside those parentheses. So I have negative x quantity cubed, negative x quantity to the 4th, tangent of negative x. Okay, so negative x quantity cubed comes out to negative x cubed. That's no surprise. Negative x to the 4th power comes out positively. That's no surprise. Now remember, tangent of negative x is negative tangent of x. Tangent's an odd function, right? So this comes out to negative x cubed minus x to the 4th tangent x. So we're going to keep a sort of a tab on that. And what we know is this, that's not equal to f of x. So since these two don't match, f is not even. maybe f is odd, and that's what we're hoping for anyway. Come down here and I see that if I just make my function negative, in other words, multiply f of x by negative, or a negative sign, then I get negative x cubed minus x to the fourth tangent x. These two match. So f of negative x is equal to negative f of x. This one's equal to this one. So I've now shown that f of x is an odd function. Since f of x is an odd function on a symmetric interval, negative pi over 4 to pi over 4, negative a to positive a, then I know that this is going to integrate to 0 thanks to the theorem above. And that's loosely based off, at least supported by these pictures that we gave to see why that's the case. So then lastly, 32, or the last example is find the average value of the function on the given interval. So the average value of a function, we have to remember what that is in just a moment. Negative pi over 3 to pi over 3 is the interval. It's a symmetric interval. And now if I wanted to check whether or not it's odd, even, whatever, I'd write down f of x equals cosine 4x, and that's what I'm doing down here. F of x equals cosine 4x. I'm ultimately going to integrate this thing, right? F of negative x is cosine of 4 times negative x. That's negative 4x in the argument, but cosine's an even function, so this just becomes positive cosine of 4x. Since f of x equals f of negative x, f of x is even, or cosine 4x is even. So now I have a symmetric interval and I have an even function. So I'm set up to use the theorem above if I should like to do so. Okay, now the average of this function is 1 over b minus a times the integral from a to b of f of x dx. Well, a and b here are given by this integral, or interval right here, negative pi over 3 to pi over 3. So here's pi over b minus a, or pi over 3 minus negative pi over 3. And then I integrate from negative pi over 3 to positive pi over 3, my function cosine of 4x dx. Okay, so this resolves to, well, this is going to be 2 pi over 3, and it's all under 1, so it becomes 3 over 2 pi. So that part simplifies as is. Maybe take a moment to sort that out. Of the same integral, same thing here. Now, by the theorem above, this is a symmetric integral with an even function, or a symmetric interval of integration with an even function. So I'll go from 0 to pi over 3 and introduce a factor of 2, right? That wasn't there before. It's here now because I'm going from 0 to 3 instead of negative pi over 3 to 3, or to pi over 3. So then these twos cancel. I'm left with 3 over pi, and I'm going from x equals 0 to pi over 3. Well, I've already done a quick step, right? I'm starting to get pretty dynamic with this stuff. U is equal to 4x, right? Because I need that to be simplified before I take the antiderivative. So in this change, I've made a note here that these are x variables, not u values, or x values, not u values. I'm going to need to change them to u values ultimately, or I have another option that I'll show you we could do otherwise. So why did I do this? U is 4x. 4x is the inner function. Du dx is 4. So dx is equal to du over 4. Right, when we solve for dx from this expression, this equation. So dx is du over 4. I look at this and I'm pretty happy with this integral. All the x's have swapped out for u's, so now I can integrate. I have a factor of 1/4, and that'll just come out front to sit underneath the 3. The antiderivative of cosine of u is sine of u. And I'm going to evaluate from x equals 0 to pi over 3. It looks like I still have not changed my limits of integration. I haven't changed them from x values to u values. If I wanted to do so, what should I do? Well, my u function is 4x. So I should do u of 0 is 4 times 0, so this would be 0. And u of pi over 3 is 4 times pi over 3, so this would be 4 pi over 3 right here. However, I've got another option. I can do this slightly differently. I can write this in terms of x again, which is really similar to just not having the limits of integration there at all, and then working my way to the end by using my antiderivative on those limits of integration. Nonetheless, this works either way. So 3 over pi 4 times pi of sine of 4x, swapping out for u again. Now that this is a function of x again, I don't need to remind myself that these are x values. I can just plug them in when I'm ready. And we're good and ready for that. So we have 3 over 4 pi is equal to sine of 4 pi over 3, the evaluation, or 4 times pi over 3, right? The evaluation of the upper pi over 3 value. And then sine of 4 times 0, the evaluation of the lower limit, or sine of 0. Well, sine of 0 is 0, and sine of 4 pi over 3, I believe that's going to be something like root 3 over 2. It's actually negative root 3 over 2. That makes sense, right? Because I was thinking 2 pi over 3, but 4 pi over 3. So they're going to 3 over 4 pi times negative root 3 over 2. And when we kind of simplify the denominators here, or at least combine numerators and denominators, we get negative 3 root 3 over 8 pi. So that's interesting. We really like functions to be odd on symmetric intervals because then we just write it down as 0. But when they're not, we do have this nice shortcut here, and we could use 0 to pi over 3, doubling instead of doing the whole interval. And maybe that's more or less useful or helpful. It might be nice to evaluate at 0 instead of that negative a value there. So there is some use to that. So that's it. We've seen quite a variety of ways of using this substitution rule. Notice for definite integrals, there are multiple ways to handle the limits of integration. What I would say is just be careful whatever you do, right? This is not standard notation. This is something that I do just sort of on my own. It's informal, but it's somewhat helpful to remind myself that, hey, I'm carrying along limits of integration that don't match the variable that I'm working in right now. And it's just a reminder, a little tag for myself to say, okay, in the end, I need to either convert these limits of integration or convert my variable back to a function of x, and then just write my limits of integration as the values that they are. So the other alternative here could have been to just find the antiderivative of this function as an indefinite integral, and then write this down. Take this step from here to here, and then evaluate. We'll know the antiderivative immediately because we've already done that as side work, and then evaluate these limits of integration times the constants. So there's a lot of versatility here. It'll just take some practice to find what you prefer to do. And that's it. That's the end of chapter 5, at least as far as what we would do. And that's it for Calc 1, at least at this course.